In the previous episode, the students created a graph of the sine function. This sine function relates an object's angle of rotation, measured in radians, and its height above the midline, measured in radii, as it travels in a circular path. In this episode, they recreate this graph by plotting different points. They begin by splitting a full rotation into 8 pieces. They first articulate what the angle of rotation, measured in radians, would be after each eighth of a full rotation. Then they show what the height of the object would be after each 1/8 of the rotation.
Okay, so there's 2 pi radians right here.
Mm-hmm.
Yeah.
2 pi. So 2 pi
Divided by 8.
So wait, 1 pi would be 4 pieces. So pi equals 4 slices.
Okay.
Slices. Okay, so each slice is 1/4 pi.
Yeah.
1/4 pi.
So each angle measure, if we cut it into 8 equal pieces, is 1/4 pi. Okay.
Yeah. So I'm just gonna write that as 0. And then this is 1/4 pi. There you go.
We just kept the denominator as 4, so like they're improper fractions,
Just
but
to make it a little bit easier.
That makes sense.
for us to
Yeah.
think.
As the students have explained, after a full rotation, an object has rotated 2 pi radians. This means that after 1/2 of a full rotation, the object has rotated pi radians, and after 1/8 of a rotation, it has rotated 1/4 pi radians. Thus, the students were able to mark in the angle of rotation at each of the 8 stops as 0 radians, 1/4 pi radians, 1/2 pi radians, 3/4 pi radians, etc. Now they will find the height of the object at these stops and create a graph.
At 1/4 pi radian, what is your height above the midline? If you could mark that in.
Would it be right here? Oh yeah, we're doing height. And then
What would the
that,
height
I'm
be?
not sure what the height would.
Use our ruler.
It's okay if you don't know what the height would actually be.
Oh, okay.
Okay.
But if you could do that for each of your
Okay.
angle measures or each of your stops.
Wait, these will both be the same on the sides.
Oh, yeah.
Wait, it'll
So
be
which are the
down
same?
here too. This is the same as that, and that is the same as that. But then that would also mean that this is the same as this, and that's the same as that. So you only need one.
I see.
Yeah.
I see.
Because it's kind of like if you fold it into fourths, they'd all like,
Mm-hmm.
yeah.
Mm-hmm.
They're all equal
Okay.
because it's an equal number.
I see.
Yeah.
Can you use your picture to make a graph?
Well, because we don't know how
Like the 1,
long.
4.
Oh, you can label that, yeah.
Which ones do you know? Yeah. So let's go ahead and mark in, like you said, mark in your radian measures.
And then
Yeah.
make it thicker so you can see what that
I was
Okay.
thinking we did. I thought you were talking about the height, and I was like, we don't really know the height.
So like you said, you don't really know the
height.
height. But what are some places that you do know the height that you could mark
There-
The
in?
maximum and minimum and the and 0 and at pi r.
Okay. Why don't you do that?
Okay. So
And
then
what
I
about at
guess
2 pi r?
At 2
2
pi r?
pi, wouldn't that be?
Oh, right. That would also be 0.
Mhm.
Thank you. Almost forgot that one existed. Okay.
Can you draw in their heights as if they were pipe cleaners, like as if you had a pipe cleaner? You can
Oh.
use a highlighter or a
highlighter.
And then I don't think we need to do anything for those 3.
No, but just this one.
Mm-hmm. Because I'll highlight them though, because there's 0.
Mm-hmm.
Okay. So if you were to see that green height, and we can call it we can imagine that it's a pipe cleaner. Where do you see that on your circle?
You see that like,
Right. The top point.
Uh-huh.
and like
Oh,
this
yeah.
middle line here.
Okay.
Oh wait, and then the zeros would be that line.
Yeah, well the zeros would be like just the dead center of it. Yeah.
Oh,
I
yeah,
see.
get
I
it.
see.
Mhm.
Okay.
Like if we were using that middle line as like a ruler kind of thing, like
Oh,
that's
yeah.
where it would be on like a ruler.
So Claire, you made a good realization. It's going to be harder for us to measure some of those other parts because we don't know the height.
That's like kind of my point. Like, I know we're not measuring in centimeters, but it's like the heights aren't going to be the same because this one's smaller.
But it's going to be the same portion of a radian. Like, even though these are different heights, the midline this to there is 1 radian, and that to there is 1 radian. So that to there is as much of a piece of a radian as this is. So they're both equal pieces of a radian.
Well, then what we'd need to find, I think I understand what you're saying, but then what we'd need to know then is, like, how, like, is the fraction of this, like, the fraction of this compared to the entire height of the radius, or like the vertical midline is what I'm going to call it from now on, I guess. We could just adjust the graph.
Oh, or we could adjust the circle.
Yeah. Either way, like we'd have to adjust something, but like.
Well, if you adjust the circle, what's happening to the radius?
It's getting bigger, but in my opinion, it doesn't
Yeah.
matter.
In your
Well,
opinion, it doesn't matter why.
Because we're measuring in radiuses,
I
not
see.
in centimeters or
Well,
inches.
and like, it doesn't matter in this scenario because, like, currently this radius is shorter than what we have here, but the only reason that is because we just kind of made a random radii, like, label here.
Mm-hmm.
So, like, if we were to match this to like make it bigger or make the graph smaller to match like each maximum, then we could have it like the same. Does that make sense?
That makes sense.
Does that make sense to you?
As the students have pointed out, the radius of the circle is not the same physical size as the length of 1 unit on the y-axis of their graph. While they decided this doesn't matter, it will be easier to determine the height of the object above the midline at various points if the radius of the circle matches the scale of the y-axis. To accomplish this, they make the circle bigger.
And then this is 1 there. That's -1.
That's a really ugly.
It's okay. And then, so what we can do now is do the same here.
Oh, yeah. Why didn't we think of this before? You're so smart.
Okay, so explain to me what this graph represents.
These are the heights. I feel like
Kinda
we went
thing.
like that and
Yeah.
straightened and then select it and brought it over. So you can measure well, not exactly, but like kind of like how we did with the pipe cleaners.
Uh-huh.
We like measured it and it's not going to be perfect, but it's closer than
Yeah.
Right. Okay. So I'm going to ask you some questions. So like this pipe cleaner here, what's that? What would that be measured in radii?
One
That is
radii.
1 radii.
Or 1 radius, I guess.
1 radius. Okay. And then this one, do we know the exact height and radius?
No.
No.
But it's just a piece of one.
It's a piece of a
Piece of a radius.
It's a piece of a radius. I'm wondering, do you think that that piece will always be the same in relation to the radius on any size circle?
I think so. That's why I thought we could use the
In
thing.
relation, yeah. Well, like the only reason I thought that wouldn't work was because like if we were like copying and pasting, then like that one could end up being bigger than like the radius that we had on here that we copied, kind of thing. That was my only concern.
I
'Cause,
see.
like it is the same ratio, but it wouldn't translate to the same height.
In this episode, Mary and Claire began to create a graph that relates an object's angle of rotation, measured in radians, with its height above the midline, measured in radii, as it travels along a circular path. They did this by plotting several points. They divided the full rotation equally into 8 stops. Since there are 2 pi radians in a full rotation, there would be 2 pi divided by 8 radians, or 1/4 pi radians, between each stop. This means the angle of rotation at stop 1 was 1/4 pi radians. The angle of rotation at stop 2 was 2/4 pi radians. The angle of rotation at stop 3 was 3/4 pi radians, etc. They then found the height above the midline for each of these stops. They decided that it did not matter how big of a circle they used to measure these heights, since their unit of measure was the radius of the circle. However, they decided to correlate the scale of the y-axis on their graph with the size of the circle so that one unit on their y-axis was literally the same size as one radius of the circle they were using to measure the heights. This allowed them to physically drag the segments they used to measure the heights on the circle to their graph. This allowed them to avoid the difficulty of estimating how many radii were in these heights. In the next episode, they explore how to use a calculator to find the number of radii in a height at a particular angle of rotation.